Well, good afternoon. Good morning. This is 11:34, 4 minutes late getting started. Sorry, I stopped by the office to try to get a little bit, eat a granola bar to make it through the morning until I had a chance to eat lunch. I only have a half hour for lunch after this class, so I want to get a little something. But then I ran into some people in the hall and various things, and also I've gotten really congested this morning. I just had a sneezing fit in my first class and have been congested ever since. So I don't know if there's something in the air, pollen, I don't know. But anyway, I'm here, but I'm the only one in the class. So hopefully some more students will be coming in. Let's get started from where we left off last time. When students come in, then I'll make any announcements they have. It sort of seems crazy to make announcements to an empty room. So anyway, picking up from where we were. My mark is that we're on page 107, chapter 3, determinants. 3.1 is determinants of a matrix. And what we're going to do is example 4 is going to be find the determinant of a matrix of order 4. Biggest one we've done so far. Let's see how to do it. Here's matrix A. Okay, of course, when they say order 4, that means 4 by 4. They have to be square matrices, otherwise the determinant doesn't make any sense. So let me get my pen set up. Okay, here's matrix A. 1, negative 2, 3, 0. 1, negative 2, 3, 0. Okay, negative 1, 1, 0, 2. Negative 1, 1, 0, 2. 0, 2, 0, 3. 0, 2, 0, 3. And finally 3, 4, 0, negative 2. 3, 4, 0, negative 2. There's matrix A. All right. We want to find the determinant of this matrix. So the determinant of A would then be, well, here's where judicious choosing comes into play. Pick the row or the column that has the most zeros in it. Dead giveaway here, third column. Okay? Now, remember, we do the minors and cofactors, all that kind of stuff. The thing to remember is determine the sign of the entry first. So we're going to use the 1, 3 entry here, that 3 right there. But if you look at that, plus, minus, plus, that's going to be a positive. So positive 3 times the determinant of the remaining matrix. So you wipe out the first row, wipe out the third column, and it's the determinant of minus 1, 1, 2, 0, 2, 3, and 3, 4, negative 2. Determinant of that matrix. Okay? Now, you could continue like we've just done, but since you got it down to a 3 by 3, again, now this is my technique. I mean, it's not mine. I didn't come up with it, but it's the easy way in my mind to do a 3 by 3 matrix. Okay? Repeat the first 2 columns. Minus 1, 1, 0, 2, and 3, 4. Okay? And then, now this isn't a determinant anymore because it's not square anymore, but you're doing the calculations for it. Go down your diagonals. Okay? And this will be, so I'm going to write this as a 3 times. This is going to be minus times minus is plus. 2 times 2 is 4. Okay? Times, this is just 9. These are pluses here. Left off the plus there. Okay. Plus 9, and that one's going to be a 0 because of that 0 in there. Then we're going to do minus is the up one, okay? So that's be minus, a 3 times 4 is 12, so minus 12. Okay, I'm going to take out these extra parentheses. They're not really helping us any. They just sort of are getting in the way. Okay. Okay. And then the next up one here is minus a minus 12, so that's going to be plus 12, and the last one's going to be a 0. Well, these two add to 0, and that gives you a 13, and 3 times 13, goodness gracious. For some reason, it just shut itself down. Let me see what keep does. All right. I don't know why it did that, but it did. So this is going to be 3 times, now it changed my ink color. So 3 times 13 is 39. There's the determinant of the matrix. Okay. I sure hope I did it right. Yes, I did. Okay. Now, let's clear this. Now, here's what I don't know. Is this going to clear? No, it won't. I was afraid of that. So, what I'm going to do is I'm going to have to end it. Okay, let's get it back again. Sorry about this. It just did something weird right in the middle of it. Now it's having trouble opening again. Okay, let's go to current slide. Yes, okay. All right, we're back again. Okay. So there's the determinant. And that's basically what you do. No matter how big the matrix is, has to be square, and then start working on it. And if you find the row or column with the most zeros, and use that row or column to do your matrix multiplication. And then that may reduce you only one size to a 3 by 3 like we had there. But then when you get down to a 3 by 3, you can use that technique. You got down to a 2 by 2, that's even easier, okay? But you just keep plugging along that way until you finish your determinant. Oh, and they do show that technique I just did, finally, at the top of page 108. I knew it was in here somewhere. I thought, I couldn't remember if that's something I picked up in another course or if they had it here. But they did have it here, and that's how they suggest doing it, and it certainly works nicely. Okay? Now, let's move on to example 5. And this is having us do what we just did. And let me get my pen back again. Every time it shuts down, it goes back to red. I don't know why the default is red rather than black. Okay, find the determinant of A. And this time A is pretty easy. It's 0 to 1, 3 by 3, 3, negative 1, 2, and 4, negative 4, 1. Okay, how to find the determinant of that? Repeat the first two columns. 0, 2, 3 minus 1, 4 minus 4. Okay, so the determinant of A would then be go down the columns with positive. That's going to be 0. Down this column, 4 times 4 is 16. Down this column, down that diagonal, I keep saying column, diagonal, that would be plus 12. Okay, now go your up diagonals. So it's going to be minus this. Let me, just so it's a little easier to tell, I'm going to erase our down diagonals here so you won't be as confused. It does get a little squirrely. So this is minus because you're going up diagonal, but that has that 1 minus sign in it, so that becomes a plus 4. This one will be your 0, and that will be your minus 6, because you're going up a diagonal, and it's positive, so that's minus 6. Okay? Well, how I would do this is any way you can. This minus that is 10, plus 12 is 22, plus 4 is 26. Okay, you could have done, yeah, anyway, 26. Let's see what they got in the book. I botched it. Okay. Did I write something down wrong? 0, 2, 1, 0, 2, 3 minus 1, 2, 3 minus 1, and 4 minus 4, 1. Must have done something wrong. 16. Oh, yes, I did do something wrong. And I think what caused it, let me erase these, was when I was doing the down diagonals, this diagonal must have wiped out my sign, so that's a minus 12 there. Okay, that's a minus 12. Okay, so let's take all those off and see what we get. Okay, don't get in too big a hurry. That's the bottom line. Here's 16 and 4 is 20 minus 18 is 2. Okay, and that's what they got. Yeah, 2. Okay. Now, the little blurb at the bottom of page 108, it's sort of a jump from the figure they show there to what they're showing over here. And by the way, this technique I just did here only works for a 3x3. Don't try it on anything bigger. You don't need it on anything smaller. Only works on a 3x3. Okay. Now, bottom of the page. Diagonal process illustrate. No, I'm sorry. Linear algebra applied. Okay. Now this looks bizarre for what the picture, and it's sort of hard to see that has anything to do with what we have here, but excuse me. Here's, and the only reason I'm stopping to do this one, this is something you could easily run into in the future. You may not, okay, but you could. What we have are 3 continuous functions. X, Y, Z are continuous functions. Continuous functions, okay? Of U, V, and W, okay, they're functions of U, V, and W. So it's X is a function of U, V, and W. Y is a function of U, V, and W. And Z is a function of U, V, and W. Okay? That first one's a U, the last one's a W. They look too close to being the same thing, but I tried to correct that one and it didn't get much better. Okay. I'm writing too fast. Okay? Now, and they also have continuous first partial derivatives. Then the thing they call the Jacobian. Okay? J-A-C-O-B-E-A-N. I believe is how it's spelled. No, I-A-N. The Jacobian. Okay, the Jacobians, and you can have it either in 2 space or 3 space. Okay, the Jacobian in 2 space, then you just don't have the third variable Z or the third variable W. So the Jacobian, and the symbol for it is J. It's a function of U and V because those are your independent variables. That is the determinant of partial of X with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Make sure I said it right. Yeah. Okay. And in 3 space, your Jacobian of u, v, and w would be the determinant of partial of x with respect to u, partial of x with respect to v, partial of x with respect to w, partial of y with respect to u, partial of y with respect to v, partial of y with respect to w, partial of z with respect to u, partial of z with respect to v, partial of z with respect to w. Okay? Now, and they tell you in some senses what they're used for. One practical use of Jacobian is finding the volume of solid region. And then it talks about 3-4 and chapter 3 review. You're asked to do some of those. Okay. Now, I'm going to say this a little prematurely. Okay. And I want to make sure it's right before I say it. Sorry, I'll get to it in a second. If you turn over to page 124, we'll get there hopefully. Section 3.3, right near the end of 3.3. If A is a square matrix, then the determinant of A is the same as the determinant of A transpose. Okay? And I was going to say that here because I'm really likely to forget whether you do the partial with respect to the same variable on top and the, oh my goodness gracious. Here we actually have a student. But it's on, I mean, it's, first,
but never last.
What's that?
First, but never last.
Yeah. And you know, I think, oh, there it is, okay. All right. Corral is here. Okay. Let me turn on projection. And turn on the light for you as well. Okay. We've already got some progress made today, so you'll have to listen to the YouTube video to catch up on it. And this is one of those little blurbs, linear algebra applied, and they put it at the bottom of the page, but they really don't do much with until maybe later. They did say some of the other examples will do this. I was just pointing out to you, or to whoever was going to be listening to this, it's called the Jacobian. And what you have is x, y, and z are continuous functions of these 3 independent variables, u, v, and w. So x, y, and z are dependent variables depending on the u, v, and w, who are the independent. Now, if you're in 2 space, you only have the first 2, x and y and u and v. If you're in 3 space, you have x, y, and z and u, v, and w. Okay? So you can do it either way, but you have to have 2 by 2, 3 by 3. Technically, you could go to higher ordered spaces, but we're not going to do that now. Okay. Now, and when I was writing these down, I was thinking to myself, it would be so easy to forget whether to have this, and I know they're not numerators and denominators, but it's easier to remind you, talk about it that way. Whether you have the same numerators on each row, and you go through the denominators in order, like I did it, and this is how it's done. Or forget and do it the other way and do partial x with respect to u, partial y with respect to u, partial z with respect to u, and then this will be partial x with respect to v. Yeah, you can do that. And as I was just saying before you came in, with determinants, the determinant of a transpose is the determinant of the matrix, as long as they're square matrices. And so it doesn't really matter, because all I did was transpose the matrix. And so you don't have to worry about it. If only you're doing the Jacobian, which is the determinant, then it doesn't matter which way you do it, either keeping the numerator, the rows with the same numerators, or the columns with the same numerators. It's going to work out the same way. But that was sort of an aside there, because knowing myself, I'd forget which way it went. Okay, and with determinants, it doesn't matter. Okay, so the next thing we're going to hit, though, is on page 109, which is triangular matrices. And I hope you remember what the triangular matrices are. You have two types of triangular matrices. Remember what they are? Upper and lower triangular matrices. Okay? Now, it says to recall from section 2.4, which I know we do so well, that a square matrix is upper triangular when it has all zeros entries below the main diagonal, lower triangle when they're all zeros above the main diagonal. Okay? Now, a matrix that is both upper and lower triangular is called a diagonal matrix. So that's sort of a new one. So I'll write an upper triangular matrix for you. Let's call it U for upper triangular. Okay? That would be A11, A12, A13, dot, A1n. Okay? Now because we're going to be doing determinants, have to have these square. In fact, I think your triangular matrices have to be square. I believe so. This one would be 0, A22, A23, dot, up to A2n. This will be a 0, 0, A33, dot, to A3n, then a dot, 0, dot, 0, dot, 0, dot, A sub n, where all these are zeros below the main diagonal. That's an upper triangular matrix. Your lower triangular matrix would be A11, 0, 0, dot, 0, A21, A22, 0, dot, 0, A31, 0, no, sorry, A32, A33, dot, 0, and this would be, dot, A n1, dot, A n2, dot, A n3, and then dot, everywhere, dot, and these would all be zeros. Oops. Down to the last one, which is A-N-N. Okay, so everything above the main diagonal is a 0. That's the lower triangular matrix. Okay? Now, as it said, if you had one that was both upper and lower triangular, then what you have is a diagonal matrix. I'm going to call it D, for lack of a better word, or letter, and that would be A11, 0, 0, dot, 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 0, 0, A22, 0, dot, 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 0, 0, 0, A sub 33, dot, 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 0, dot, 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 0, dot, 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 0, dot, 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 0, dot, 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 A sub n, n. So the only thing that's not 0 is your main diagonal. Those are the only non-zero elements in a diagonal matrix. Okay. Now, what they're asking us to do here, to find the determinant of a triangular matrix, simply form the product entries on the main diagonal. So let's do, here's a matrix A, which happens to be, well, I'll write it down, 2, 3, negative 1. 0, minus 1, 2. 0, 0, 3. Okay? What's the determinant of that matrix? Well, it is a 3 by 3, so you can do it the old simple way, and might as well do it. Why not? Okay? And by the way, the book did show this method. Later, I've been showing you already, but they finally showed it to you on the previous page here. Repeat the first two columns, 2, 3, 0, minus 1, 0, 0. Okay? And we're going to do a determinant, even though this is not square. You're just going to do, so here's your main diagonal, and that produces a minus 6, right? But then when you do this diagonal, you get a 0. You do that diagonal, you get a 0. This up diagonal, you get a 0. That up diagonal, you get a 0. And this up diagonal. Everything's a 0 except the main diagonal. Because all these features down here are zeros. And when you multiply anything else by it, it comes out as 0. So the only thing that doesn't contain a 0 is that main diagonal. Now, if it does, then that whole matrix is the determinant is 0, which means it's not a invertible matrix, because the determinant of a invertible matrix has to be non-zero. Okay, so only for any upper or lower diagonal matrix, or certainly upper or lower triangular matrix or a diagonal matrix, the determinant of every one of those is the product of the diagonal entries, period. And if any one of the diagonal entries is a 0, the determinant is 0 and it's non-invertible. Okay. So, and I came up with minus 6. They did it the long way and came up with minus 6. So that then leads, you need that a little bit longer, or are you okay with it?
Yeah, I'm fine.
Okay. So here's theorem 3.2. If A is a triangular matrix, doesn't say which kind, upper or lower, it doesn't matter, of order n, meaning an n by n square matrix, then its determinant is the product of the diagonal entries, period. Nothing else. Okay? The main diagonal. Okay? So the determinant of A is equal to the product of A11, A22, A33, dot, 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 up to A, N, N. Only those entries, the product of those. Okay. Now they have a little proof there. Certainly, if you want to go through that, you can. It uses cofactors in the minors and all that kind of stuff, but what we did earlier showed it. So let's do example 6. Do you need this any longer?
No.
Okay. Example 6. The determinant of this lower triangular matrix, A is equal to, no, it's probably don't shut it off. No, it didn't. Okay. Is this matrix here. 2, 0, 0, 0. 4 minus 2, 0, 0. Negative 5, 6, 1, 0, and 1, 5, 3, 3. Okay, what's the determinant of A? It is a 4 by 4 matrix, which is okay, but that doesn't really enter the picture too much here. What's the determinant of that matrix? Except it has to be square, and yes, it is a square matrix. So what's the determinant of that matrix?
I'm going to write down the diagonal.
Just the product of the diagonal entries. You're absolutely right.
Oh, it would be 8.
Product.
Oh, it's not a thing. You said 1 from 8, but I'm going down. So, maybe 4.
It's the product of your diagonal entries. Right there. Those are your main diagonal, right?
Right.
Okay. And the product. Now here's how I do products of the groups of numbers like this. I first count my negative signs. How many you got?
1.
Negative signs. 1?
1.
Okay. If it's an odd number, the answer is going to be negative. If it's an even number, it's going to be positive, right? So we have 1, so it's going to be negative. So I'll write down the minus. Okay? Now, multiply those numbers together. Forget the signs, the number. 2 by 2 is 4, times 3 is 12. Right?
Right.
Negative 12. Times 1 is negative 12.
I think I was adding.
Well, it looked like you multiplied the 3 and the 2 and got 6 and added 2 to that and got 8. That's the only way I could figure you did that, but I didn't know if that's what you did.
That's how I got 8.
Okay. But you multiply them, not add them. You not multiply and add. Multiply, yeah. Okay. So there's that one. Now they string it out. I'm sorry. No. They did exactly what I said, just multiplied the diagonal entries and got a minus 12. Good for them. And that finishes 3.1. So homework exercises here, do any of the odds 1 through 11. And by the way, all the odds are, you can go to calcchat.com for worked out solutions to the odd numbered exercises. So any of the odds 1 through 11, either 11 or 15 or both. Do 17. Any of the odds 19 to 31. Do 33. Any of the odds 35 to 30, either 35 or 37. Either 39 or 41. Do 43. All right. Do either 45 or 47. 49 or 51. 53 or 55, I'm sorry, any of the odds 53 to 57. Do 59. Any of the odds 61 to 65. Do 67. And do 69. Okay? And here we have Muhammad. All right. All right, we just finished 3.1. All right. All right, clear?
Yes.
Okay. Now, 3.2 is the determinants and the elementary operations. Can anyone remind me of what are the elementary operations that you can do with matrices? The elementary operations, elementary matrix operations. Swap any two rows. Second.
Do a single operation? Do a single operation?
Yeah, what are the three elementary row operations that you can do with a matrix? One is swap any two rows.
Swap any two rows, multiply by a constant.
Multiply any row by a non-zero constant. Never go around multiplying by zero, ever, okay? Nor divide by zero.
Yes, you need, you just want to get rid of everything.
Yes, exactly, but then you lose all meaning, okay? So multiply or divide by any non-zero number. That's number two. And the third one? It's the one we use the most. Adding a multiple of one row to another row.
Oh, yes.
Yeah, okay. So those are our three elementary row operations, okay? Now, how do those affect our matrices? Okay? Now, here we have two matrices, determinants of two matrices. Here's the determinant of A. That would be the determinant of 1, negative 2, 3, 1. 4, negative 6, 3, 2. Negative 2, 4, negative 9, negative 3. And 3, negative 6, 9, 2. Okay, what if I told you you had to do the determinant of that matrix, or you could do, if you prefer, the determinant of this matrix. It's all, determinant. One, negative 2, 3, 1. 0, 2, negative 9, negative 2, 0, 0, negative 3, negative 1, and 0, 0, 0, negative 1. Okay, good to see you. Jordan's here. So the last half of the alphabet, perfect attendance. The first half, not a 1. Okay, so way to go, you guys. Okay, if I said you could do the determinant of either one of those two matrices, which would be easier? Say again? First or second? Second, by a long shot. Can anyone give me the determinant right off the top? Of the
Divide second over by 2.
It's what?
Divide second over by 2.
No. Give me the determinant of that matrix. Say again? 6, exactly. Okay? Now, you came in after we did this, both of you, the last two did. If you have a triangular matrix, this happens to be an upper triangular matrix, where every entry above the main diagonal, every entry below the main diagonal is 0, or a lower triangle would be every entry above the main diagonal would be 0. If you have either one of those, or just a diagonal matrix, that's all you got. That is not 0 is your diagonal. Any one of those three, upper or lower, because the diagonal matrix is both upper and lower, you just multiply the diagonal entries together. So that's what he did. There's two minuses, that makes a plus. Multiply the numbers together, you get 6. Okay. So the determinant of that matrix is 6. Okay. Now this one, real pain in the neck, because there's no zeros in any row or column, so you have to go through and slug through and do the whole process. Okay, now, so what? Well, given what you know about determinant of triangular matrix, it's clear the second one is much easier to evaluate, which we did. That gave you 6. Let's do the first one just because they're doing it in the book. Okay, now, and we haven't done one of these lately. Okay, and by the way, Jordan, have you gotten either of the first 2 tests in here? You have or have not got the second one? But you have the first one. Okay. Be sure you get the second one before you leave today. Okay. Because this chapter 3 is really short, so we're going to have the third one really soon. Okay. All right. So let's do the determinant of this one. That's what chapter 3 is about. They choose to go use the top row, which is just as good as any. There's no zeros in any of them, so let's use it. Well, we start right here with the first one. 1 is in a plus position. You start at the upper left corner and do plus, minus, plus, minus, plus, minus. It always starts as the plus. So the determinant of A would be 1, that's because that's positive, times the determinant of this matrix here. Minus 6, 3, 2. You wipe out the first row and first column. I did it backwards, but whatever. 4, negative 9, negative 3, negative 6, 9, 2. Well, since that's a 3 by 3, we can do that by repeating the first 2 columns. Minus 6, 3, 4 minus 9, negative 6, 9. Okay? And then do it, our technique for doing this. This isn't a real determinant, but it gives you the answer for it. You do the first element down, and this is going to be 1 times, I could leave off that. And that's obviously positive. That's 54 times 2 is 108, right? All right. Keep coming. All right, finally have a top part of the alphabet person here. Okay. Daniel's here. Okay. Is everybody with me on this? 54 times 2 is 108. Then do the next diagonal, and that's going to be minus, or 18 times, or let's do it this way. Positive, okay, and you got 9 times 6 is 54, okay. Then the next diagonal is also positive. That's 8 times 9 is plus 72. Okay. Now we do our up diagonals, which are negative. Well, that's 54 times 2 is 108, but it's a minus, so it's minus 108. Next up diagonal is going to be a minus, because you got 2 minuses there, but then going up is a minus, so that's 3. And that's going to be 54 times 3. I think that's 162. Someone check me on that. 54 times 3. I believe it's 162. Is that right? Okay. And then this one is going to be a minus, and that's going to be 24. Okay. Now, easy to do is eliminate the 108s and add these two together, and you get a 126. Add these two together and you get a minus 1 86. Combine those two together, you get minus 60. So this is a minus 60. 1 times minus 60. And we're only a third of the way there, okay? Then you do the second entry here. Yuck. Okay. Okay. So you're going to wipe out the first row, second column, and do the same thing again. Okay? So the first is a minus 60. Now the second one, just as a review, is a minus 2 up there, but it's minus 2, but that's a negative value, right? Negative entry point. Plus minus. So that's a minus place, so you do a plus 2. So you do a plus 2 times the matrix that's left over there, and you just do the same thing with that, expand it and multiply, blah, blah, blah. Then you do a plus 3 times its minor, and then you do a minus 1 times its minor. Okay? And they just take a lot of room and a lot of effort. I'll leave you to doing those, but they do them in very shorthand in the book, and they came up with a minus 60 on the first one, plus 78 on the next one, minus 30 on the next one, and plus 18 on the next one. And when you add all those things together, you come up with 6. The same as we had just doing the main diagonals. Okay? This is a lot more work. Okay? Now, how did we get from A to B? We did our row reductions. Okay? We did our elementary row operations. All right. Okay. Here's something they point out to us. I don't know if you noticed it or not, but if you go back up, no. I'm going to erase my construction lines here. I thought I was going to erase my construction lines here. It's still not erased. There it goes. Okay. And we'll ignore the last 2 columns there. We really don't need them anymore anyway. So get rid of those. Now, here they, whoa, goodness gracious. I erased the wrong ones. It doesn't matter. Let me, I'm sorry I did that this morning, and then could not stop my nose from running the rest of the day. For some reason, I can't get my eraser. There it came up. Okay, I erased the wrong construction line. Sorry. Those. Now, here was the thing they said they didn't know if you noticed it. Okay? If you subtract row 2 from row 1 here, make sure I copied it right. Yep. I don't know how they got row 2. That's what I was assuming they did. Subtract this from this, you would get, you get a 0, a 4, a 0, and a minus 1. That doesn't look anything like theirs. Okay. But if you multiply this row by 2 and add to this row, I'm so sorry. because there's only two. So I have a squeezing fit, everything loosens up. So multiply this by 2 and add it to that row. This gives you a 0. That gives you a 0. This gives you a -3. And that's what you get there. And this gives you a -1. And that's what you got. So that row comes out really nicely. And if you multiply this row by -3 and add to this one, you get a 0, a 0, a 0, and you get a -1. So that's how they got these two rows. I still haven't quite figured out how they got the second row. It looks like they did it wrong, but it doesn't really matter. Well, it does matter. Because you got a different number here than you would have otherwise. And
I think they might have multiplied -2. No, that's not it. It's not.
I can't quite see how they did it, but they came out with the same thing. Note that A and B have the same value. Also note that the obtain matrix B from matrix A by adding multiples of the first row to the second, third, and fourth rows. Oh, I did mess it up. This is a 4 here, not a 1. 4, -6, 3, 2. Okay? Now, if you do that, multiply 4 times, -4 times this row, add to that. That gives you a 0, a 2, a -9, and a -2. Yeah, that's how we got it. That was a 4, not a 1. Sorry. It helps to copy them right. Okay. So, yeah. So all we did was one simple row operation, elementary row operation, adding a multiple of one row to another row to get your diagonal matrix. Okay? And then, sure enough, you wound up with the same determinant. Okay? Now we'll get why in a minute. Let's do example 1 first. Okay. Yeah. Okay. The determinant of A being 2, -3, 1, 4. 2, -3, 1, 4. Make sure I copied right. What's the determinant of A? This one's easy. What is it? 8. More than 8. 8's the first step.
Am I doing a -3 and 1, 2? Or just...
Okay. All right. If this had been a 0 here, 8 would have been the answer. Then this would have been an upper trying
So
to
do
go
you
later.
turn down into 0 first before you multiply the...
No, okay. What I'm saying is, what is the determinant of A? It's a 2 by 2. They're easy. You do this minus that.
Oh, yeah.
Just like before, the main diagonal, the product of the down diagonal minus the product of the up diagonal. What does that give you?
11.
11. Perfect. Okay. That gives you 11. Okay. That's what they got in the book too. Now, here's matrix B, determinant of B. Now, B, what they, well, 1, 4, 2, -3. 1, 4, 2, -3. What its determinant?
Is...
Second?
5?
No. Okay. Negative 11, perfect. Okay. Now, how did you go from A to B? Yeah, you flipped 2 rows. So, here is a rule for elementary row operations. If you exchange 2 rows, you negate the determinant. Okay? You just change its sign. Okay? Every time, no matter how big or how small the determinant is, the matrix is a square matrix. If you exchange 2 rows, you come up with the negative of the determinant. Okay? Now, the B part. We have determinant of A. Well, I couldn't have done the same one, but they didn't. 1, negative 3, 2, negative 4. 1, negative 3, 2, negative 4. What's this determinant? Negative 2?
Is negative 4 plus 6.
Yeah?
So, yeah, it's negative 2.
Is it? Negative
No,
4.
it's 2.
2. All right. 2.
I'll put the negative.
All right. All right. You're just being negative today, aren't you? Okay. Here's B. 1, negative 3, 0, 2. Even easier. What's that one?
It's 2.
That's 2. Okay. How did you get from A to B? Well, if you multiply the top row here by minus 2 and add it to that one, that gives you a 0, and that gives you a positive 2. So yeah, when you add a multiple of one row to another row, it doesn't change the determinant. Which goes back to the one we did originally, a 4 by 4. That's all we did on all 4 of those is do a multiple of one row added to another one. Did not change the determinant. And here you don't either. Okay? Now, here's another one. 2, negative 8, negative 2, 9. 2, negative 8, negative 2, 9. Okay? What's this determinant? Did I hear that?
It's 18 plus 16. That's going to be.
Okay. How did you get that?
2 and 9.
2 times 9 is?
18.
18.
18 minus 16.
Yes.
It's not 18 plus 16. 18 minus 16. We need 18 plus 16. That's got it. It's 18 minus 16. That gives us 2.
2. All right. Whew. Took a while, didn't it? Now, what you think we're going to do to this one? Divide the top row by 2, right? 1, negative 4. That's an elementary row operation, right? Negative 2, 9. Right? What's its determinant?
It's going to be 9. 9 minus 8.
Is 1. So when you...
How do we get from 2 to 1?
Okay. How do we get from here to here? We divided the first row by 2. That divided the determinant by 2. So when you multiply by a non-zero number, 1/2 was our non-zero number here, you multiply the determinant by the same non-zero number. So if you exchange 2 rows, you change the sign of the determinant. If you add a multiple of 1 to another row, keep the determinant. But if you multiply one row by a non-zero number, you multiply the determinant by the same non-zero number. Okay? And that will give you your determinants. So those are the three rules. Let's formalize that in the theorem. Okay? Let A and B be square matrices. And they didn't say this, but they have to be of same size. N by N, whatever that happens to be. Okay? One can't be N by N, the other one M by M. Can't work. But they should have really said that. Okay. Excuse me. All right. If that's true, number one, when B obtained from A by interchanging two rows okay, of A, then the determinant of B is equal to minus the determinant of A. If you just interchange two rows, you negate the determinant. Okay? Number two, when B is obtained from A by, goodness, I can't even, I just wrote it and I can't read it now. Interchanging two rows. Okay. This time when B is obtained by A from A by adding a multiple of one row to another row then the determinant of B is equal to the determinant of A. Okay? And the third one, when B is obtained from A by multiplying a row of A by a non-zero number okay, C, okay, then the determinant of B is equal to C times the determinant of A. Okay. Now, you can go through and follow their proof. It's pretty straightforward. All right. Let's see if we can do example 2 now. By the way, there's a little blurb here on Augustin Louis Cauchy. I guess is how you pronounce his name. I've never quite figured out how you pronounce that. Cauchy, Cauchy, Cauchy. I don't know how you pronounce it, but I think it's Cauchy. And it, by the way, it mentions Cayley's work, which we already have had a blurb about him. Either one of them would be pretty good topics for your research paper. And how many do I have research papers done by all the people in this class? All 7. Uno. 1. And guess what? We have less than a month left.
When do all grades have to be?
When do what?
All grades have to be.
Okay. That leads to something else. I was going to make these announcements. I forgot to. Well, I didn't want to at the beginning because no one was here. But to answer that question, I'll go to the administrative calendar, which I happen to print off this month. The first day for final exams is 4 weeks from today. 4 weeks from today is the first day of finals, which means we only have 4 weeks of class left, then finals. Okay? So our last day of class is Thursday the 25th. And here's some other bad news. Next Thursday the 11th, they have honors and awards ceremony over on the Birmingham campus starting, I think someone told me this morning at 10, and it's not going to be over by, this class starts at 11:30. It may be over by 11:30, but I'm not going to be back over it because it's on the other campus. So if we have a class, it's going to be a short class. And if I can get back here before 12:45, I will have class for the remaining few minutes, whatever that is, 5 minutes, 10 minutes, 15 minutes. I'll have class, but it's not going to be a full class. So that means we have very little class time left. You only have 1, 2, 3, 4 weekends left before the final exams. That means for getting your papers done. So please get your papers done, your test in, that kind of stuff, because finals start on the 30th. Now, to answer your question, they only go through April. The last for grades to be in, that will be in May. And my guess is, since finals are going to go through May the 4th, 5th, 6th, I'm guessing the last day of finals is May the 6th. That would put grades being in probably May the 8th. Is when I'm guessing grades are due in. Second?
Graduation on the 10th.
I'm sorry. And graduation, I think, is on the 10th. Is that right?
So that's for graduates too? That's for graduates too?
As far as I know, I haven't seen anything that's specified differently.
Okay.
Yeah.
Thank you.
Yeah. Now, that was the first announcement. Another one, and this is actually on this calendar, but it seemed like it should be. Does anyone know what tomorrow is? L Day. Okay?
Oh, yeah.
It's Lawson Day. That's when they have music, they have food, they have games and that kind of stuff. It shouldn't interfere with classes. We're going to have class just as normal, but in between classes you can go out and listen. In fact, in class you'll hear the music out there. So anyway, tomorrow is L Day. I'll make the rest of the announcements as it comes sooner. And by the way, online registration for summer term, they say starts next Monday. Though I have seen some people have already started registering, but officially begins next Monday. Okay, I'll get to the rest of these later. Have any of you heard of NCAS, NASA Community College Aerospace Scholars? Okay. Daniel, did you participate in this one or a different one? Okay. You're a NASA scholar,
Yes.
aerospace scholar. Okay. You count it a pretty good program?
Yeah.
Okay.
Do they give stipend?
Do they do a stipend is his question. Do they pay you?
Oh yeah.
How much?
For the NASA Scholar thing, you have to take that as a part of it. And
Yeah.
500 a month.
Doesn't pay the bill.
Okay. But you count it a good program?
Yeah.
How long was the program?
Huh?
How long was the program?
This one starts in fall, and does it go all year? Or one semester or what? How long did yours take?
That in-class class lasted a little over a month.
Oh, a little over a month. Okay. When did you do it? Last fall or this term?
I think he's talking about.
Last time.
Last fall. Okay.
Are you talking about the STEAM program being covered every month, or are you talking about this program?
This one. And this is dealing with STEM, but this is NASA. They have all these
No, I'm
programs
asking,
of it.
this program they give you covered every month, or the STEAM program give you covered every month? When you get 500 a month?
The NASA program, right? NASA scholars.
They give
Yeah, that's just part of it. To be
this.
Participant.
to qualify for it,
Yeah.
you have to take that.
Okay.
Yeah.
Okay. So let me tell you this. You can go and search on NCAS, NASA, community college, aerospace scholars. You can do it. I can give you email addresses, website addresses here. You can get them off there. Any way you want to do it, find out about it. It's a great program. Look into it. Okay? And then there was one more. Oh, do any of you go to the Birmingham campus ever? Fridays? Okay. If you ever ate on the Birmingham campus in the Leon Kennedy Center, they say here the Leon Kennedy Student Center is now closed. Okay? All the food services, all the programs, all the bookstore, the Space Center, everything that was in Leon Kennedy is now in the new Academic Success Center that they talked about right now. That new building. Everything's there.
Why they added the price of the food in there? Because of the building?
Well, no, actually two things happened. The new building happened, but the other thing is, I think at the beginning of this term, they went to a outside vendor. Our bookstore, that's actually Follett Books. It's not Lawson State Bookstore. It's Follett. Several years ago, we owned the bookstore and everything was cheaper. Then Follett came in to make it better and made it more expensive. Well, they're doing the same thing with the food service. We used to do our own food service. Then they brought in this outside thing. It's now a gourmet thing, and of course that's more expensive. So that's the main reason. The new building may be adding to that too. I don't know. Yeah, I haven't eaten at it since the change. Probably haven't bought anything at the bookstore since the change, but I do have to order books through them. But anyway, it's all this privatization stuff. Okay. Anyway, we have just eaten up the last of our time, haven't we? So we didn't get to do example 2. All because I went off onto my commercial. Okay, but we'll begin with example 2 next time. Okay? All right. Now, did we do enough for a homework example? I think maybe so. I think you can do... You can do some of the odds on 1 through 19. If you can't do them all, at least look at them. I think you can do all those. Any of the odds 1 through 19. We'll pick up the rest of those next time. Okay, good deal. And we did run out of time.